Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are coming to the last lecture on the Ising model and its analytical properties. So it's a nice place to start by a quick review of what we have done. So in the last meeting or in the last lecture, we had discussed the series expansion method. And the idea was to identify some small parameter around a known solution and try to find the physics around that regime by using some small parameter that emerges. In the high temperature regime, we identified the thermal probability of excitation of a single spin as the small parameter, and we were able to organize the expansion in terms of the number of flipped spins. We also realized that we can sort of, both for calculational purposes as well as for physical insights, draw diagrams to indicate the kind of excited states that we have, and those diagrams organize themselves into connected and disconnected pieces. And we found that only the connected pieces with the correct powers of the system size will contribute to the free energy, and there is a magical cancellation of the disconnected pieces to get to this answer, which is a very interesting result. Based on the calculations we performed, we were able to find an expression for the free energy at low temperatures, and we were able to extract some physical quantities regarding the ferromagnetic phase. So what will we do in this lecture? So of course we have done the low temperature physics. So natural place to look for is the other limit where T is much greater than J. So you could also think of this as the J equal to 0 limit. This is the limit where all the spins are sort of isolated from each other. And then I'm going to turn on J, if you wish, so that J by T is a small parameter and I can try to do some kind of expansion. And ultimately, we'll take a fresh look at duality, and you will hopefully be a bit surprised by what we find. Okay, so we'll start with setting out the notation and so on. So we have again n sites. So it's a L tilde by L tilde square lattice with periodic boundary conditions. Spin configurations are described by C, and the set of spin values at each site are collected together to form one configuration. The Hamiltonian is given by this. It's a ferromagnetic Ising model with nearest neighbor interaction, and at high temperature, this implies that the K, the dimensionless coupling constant which enters the partition function, J by T is much smaller than 1. Okay, so I'm going to just set the problem in a slightly different language than the sites. So I have to use link variables, which we have used many times in the course so far. So if I look at the lattice, L is a link on the lattice, and this mu L here, that is the product of the spin value on the left side here and on the right side here. So I'm just calling IL1 and IL2 as the sites that border the sites that terminate the link L. So if you give me a spin configuration, I will tell you all the link variables by doing this calculation, and there are 2 n link variables. Okay, this is fairly obvious. We have also seen this when doing the duality calculations. Okay, so the partition function, which originally is written in terms of the site and so on, we can now write as a product over all links exponential coupling constant K times the link variable. So this is something we have seen when we were studying duality. Okay, so where do we take off the high temperature expansion from here? Okay, so this is the partition function. Let me walk you through this. So it's the sum over all spin configurations, the product of exponential K, the coupling constant, times this link variable. Remember, give me a configuration, I'll give you all the link variables. So these link variables are actually dependent on the spin values. Now, recall e to the I k mu l, because mu l's take values plus and minus 1, can be written in this form: cos k, cosine hyperbolic k, plus sinh k, sine hyperbolic k, times the link variable. Okay, now what I am going to do is I am going to take the hyperbolic cosine k factor as a common factor and pull it out of this parenthesis. And how many terms of cos k will I get? I will get 2n terms, because there are 2n links. So I will be able to pull out a factor which is cos k to the power 2n. So this of course doesn't depend on the spin configuration, so it just comes out of the full sum and it just is a factor on this term. And here again I have the product over all lengths 1 plus tanh k times mu l, and this has to be producted over all links, and I have to sum over all the spin configurations to get my partition function. So when t is much greater than j, this k is much smaller than 1, and little t, this is our definition, which is equal to tanh k, is a small parameter. Okay, so we have found a natural small parameter at high temperature, and what we can do is we can now expand this in powers of little t. Okay, so I'm expanding. So what I'm doing is I have this sort of what we call analytical factor. It's a kind of boring. It will not give you any interesting physics at a finite temperature. So it will just contribute to some analytical piece of the free energy. So I just divide it off from the partition function. I can always put it back. I'll see that that quantity is the following. So you see there are 2n terms in this product over all links. So what I'm going to do is I'm going to think of tanh k as little t, and I'm going to expand the product of 2n terms. So what will I get? When I take 1 from each of the product, I will get 1 plus, if I take t, if I want to find what is the term to the power t, I have to take one term corresponding to the mu l term from one of the 2n terms, and from the rest of the other 2n terms, 2n minus 1 terms, I take 1. So that will give me this term, which is sum over all mu l, sum over all links mu l. And t square will give me a term where I have to sum over all pairs of links which are distinct. All pairs of links which are distinct. That's what we mean by saying L1 not equal to L2, mu L1, mu L2. So here what I do is, from 2n minus 2 terms in this product, I take unity, and only from 2 terms I am going to take t times mu l terms. And so you will see that there will be that many terms and so on. So you can expand this, and the last term in this expansion will be t to the power 2n, and that is the term where you will pick out t times mu l from all terms. So you will get t to the 2n because there are 2n links, and the product of all the link variables on all the links. So that's what it is. I think it's pretty straightforward. So let's move on. Okay. So now what I have to do is I have to sum over all the spin configurations. So you see there is the sum over all spin configurations sitting outside here. So I'm going to push that into this. So what I'm going to get is I'm going to get t power 0, which is just 1 times sum over all spin configurations of the number 1. I'm just going to call this W0. Then there is t, and whatever shows up here I'm going to call W1. And that is t square, W2, and so on, and all the way up to W, capital W to the 2n. Okay. Now, if you pause for a moment and think about what these objects are, they have no coupling constants or anything in them. These are sort of numbers that depend on the kind of lattice, in our case square lattice, and the fact that you have Ising variables on the lattice. So for example, can you guess what W0 is? If you found that it is 2 to the power n, congratulations, that's the correct answer. Can you guess what is W2n? Okay, I'm not going to give you the answer for that. Okay. So again, these objects are simply some numbers which depends on the lattice. Okay, we know what W0 is, that's an obvious answer. Let's figure out what are the numbers W1 and so on. So our problem of finding the series expansion at high temperatures for the partition function is reduced to some kind of combinatorics kind of problem of just evaluating these objects on a lattice. Okay. Okay. So the central idea that comes into the calculation of WM numbers is realization, the obvious realization I should say, that the mu-L products, if you product mu-Ls, what you're going to do is you're going to get product of spins, right? Okay, so let's try to compute W1. So what is W1? W1 will have a single link, and therefore mu-L will be the spin at this value multiplied by spin at that value, summed over all possible spin configurations of the system. There are 2 to the n spin configurations. You have to sum over all of them. So now you will realize that if I take this mu-L and take spin at this value multiplied by spin at the other value and sum them, you will simply get 0 because there are. So let's look at the configurations. +1 +1, so that gives me +1 term. +1 -1 -1, 1 -1, -1 +1, -1 again, and -1 -1, which gives me +1. So it is the total answer for this W will be, when I sum over all the mu-Ls, summing only over these spins. Remember, I have to sum over the other spins as well, other spin values as well. Okay, just worrying about summing over all these spins, I will get 0, 1 -1 -1 +1, and I'll get 0. Wow, so W1 is already 0. Okay, what about W2? So W2 will have 2 types of links. There are links which will show up on separate. The links are such that they don't share any site. Because they don't share any site, exactly the same reasons that we gave for why W1 equal to 0 will apply to these kind of terms. And this will also, any such term, if you take any such link and find mu-L1 and mu-L2 and just sum over all possible spin configurations, you will get 0. Okay. What do you think will happen to this? So what happens, this is quite interesting. You see this spin here, the spin on this side will appear 2 times. The mu-L corresponding to this will give you one value of one term associated with that spin, and the mu-L corresponding to this will give you another term corresponding to that spin. So you will get a spin value at the site square, which is always 1. So this fellow simply drops out, and this kind of a term will be simply product of spin here and a product of spin there. And by the very same argument we used to show that the sum over mu-L of a single of overall all spin configurations will vanish can be applied to this case as well, and that will also fall out of the calculation. Okay, so that's the result. Okay, so we have found that W1 is 0, W2 is 0, and if you just think about this for a moment, you will realize that W3 also vanishes. So this is looking ominous now, because how far can we go, right? You'll see W3 is again 0 because this terms will be 0, this terms will be 0. If all three get connected, for example, if I, instead of having this link here, I had that link, then these 2 spins will drop out, and it will be, the term will be just product of this spin and that spin, and by the same argument that will also vanish. So all the terms seem to be going to 0. Okay, let's look at what happens at 4. Now you see, again I have all these disconnected terms here, right? All these sort of terms here. There are 4 links. All such terms will vanish. However, we encounter a picture like this. So all these are 4 distinct links. So now you see this link is sharing a spin with this link and so on, and the other link. So now when you look at what mu1, mu2, mu3, mu4 are, it will turn out to be square of the spin value here, square of the spin value here, square of the spin value here, and square of the spin value here. So it will all square to 1, and this term will not depend on the spin configuration at all. And therefore, it will add up to give me an answer of 2 to the power n when I sum over all possible spin configurations on the lattice. So I had to go to the t to the 4 order to get a first non-zero term, and this is the first non-zero term. Okay? Alright. Now you will immediately realize that I chose these 4 links to get a non-zero term of 2 to the power n. But I could have chosen these 4 links. And in fact, if you will realize that there are n distinct ways of choosing such squares, they are just the plackets. There are n distinct plackets of my square lattice. So I have n distinct small plackets of my square lattice, and that gives me that there are n such terms. Okay. So we have done up to 4, and what are the lessons we have learned from doing up to this order in evaluating these W terms? Okay. So suppose I want to evaluate the product of m such mu's. So I am thinking of a term that multiplies t to the power m. So first observation is that what you have to do is you tell me which are the links that you want to put these m your choice of the m links. You go to the lattice and draw lines like what I have done here. Okay, just draw lines on the lattice corresponding to the links. Now you list out all the sites in your lattice which have been touched by one of these lines that you have drawn. So for example, in this picture, this site is touched by this link, this site is touched by the same link, this site is not touched by any link. So no, 0 links are touching that site. This site is touched by one link, this site is touched by one link. Okay. Now look at this problem. You look at this configuration. This particular site is touched by 2 links, whereas this site is touched only by 1 link. So in any such configuration of the choice of link values here, you can have different types of sites which are touched by some number of links, sites which are touched by another number of links, and so on. Now if I look at this particular configuration, you will see that every site that is touched by links is touched by 2 links. Okay. Whenever a site is touched by 2 links, in the term, the spin at that site contributes as a power of 2. If it is touched by a single link, then it will only come as a single power. The spin will show up as a single power. So in other words, if you have, after drawing these link pictures, if you find that there are sites which have an odd number of links touching it, even a single site with an odd number of links touching it, then that term will vanish. Because when I sum over all spin configurations, I will have a single power of this spin, and that will simply add to 0, and you will get the full term vanishing. For example, if I have a configuration in which 3 links touch a given site, that again will give me 0. But if I have 2 links touching a site, then it may or may not be 0 depending on what other spins involved are doing. So if every spin that is touched by a link have even number of links touching it, then I will find that term will be non-zero. In fact, its answer of summing over all possible spin configurations will be again simply 2 to the power n. Okay. Okay, so that is how you evaluate these terms. What else can we say? Now you will see that each of these terms, anytime you are able to draw links on the lattice which have the property that the sites that the links touch will have even number of links touching them, that will give you the answer summing over all configuration 2 to n. You will find that there are many other places where you can decorate the links in the way that you will get the 2 to the n answer again in a different way. So we can call that as the degeneracy of this sort of link configuration, right? Non-zero terms can be connected or disconnected, just like in the case we have when we did the low temperature expansion. I'll illustrate this in the next slide. But before I go further, you can pause and confirm for yourself that this statement is true. Because of all these properties, every instance I am summing over link configurations of an odd number of links, I will always get 0. Because if I have an odd number of links, there will certainly be a site which has odd number of links touching them. Okay. So all WMs for M odd are 0. Okay. Now we have to evaluate these WMs. I am going to show you at the T to the 8 order. That means each term that I am going to compute will have 8 links. And I will also illustrate for you the idea of degeneracy, the idea of connected and disconnected using this example. Okay. So now you see, I have connected terms. So what are the connected terms? I have to put 8 links on the lattice which are distinct links. So look at this particular example. So they are going to touch a bunch of sites, and whichever site that the links touch, there must be an even number of links touching the sites. So you can check that for yourself in this picture. Every site that the links are touching, there will be 2 links touching the site. Okay. So I start here and you can count 1, 2, 3, 4, 5, 6, 7, 8. There are 8 links, and that's why this is W8 diagram. How many such diagrams are possible? You will see there are 2n of them, because if I think of this bottom left corner of this diagram as the origin, I can choose this origin in 2n ways. Why 2n? So I should say I can choose the origin of this in n ways, but I can also orient this along the x-axis or orient this along the y-axis. So that will give me 2n. Now this diagram also has 8 links, and they satisfy the condition that every site that the links touch has even number of links touching them. And you will see that the degeneracy of this is 4n. And if you look at a term like this, that is also this one also has 8 links that are multiplied together, and you will see that the degeneracy is n, because you know the center of this square, the big square, can be chosen in n different ways. So this is what we get for the connected diagrams. What do we get for the disconnected diagrams? Now at W8 order, where I have 8 links, I can realize 8 links which satisfy the condition that every site that the links touch have even number of links touching them. I can realize it in this way. Now you see, this are disconnected pieces. So you will see that this again is the square that we have seen at the W4 order, and this is a product of 2 W4 order terms if you wish. And now you can see that since they shouldn't be adjacent, you can choose this again in n times n minus 5 by 2 ways by very similar arguments that I gave when we were discussing the low temperature expansion. Okay. So this is the way we compute the W terms. right? So we have now completely figured out, if you give me some Wm order, I can sit down and I can figure out all these sort of distinct connected terms I can write down. I can find out disconnected terms and so on, and I can do sums. For small m's, maybe we can do it by hand. If you go to larger m, probably you need to use some computer program or something. Okay, so the W8 term that will enter the partition function calculation will be, you find the value of this diagram and just multiply it by the degeneracy and add them all together. So all of these terms will be multiplied by the degeneracy and added together, and that will give you the full W8 term. Okay, all right. So we have come this far. So now we can put all the stuff that we have studied or explored so far and try to compute the partition function. Okay, I had already let the cat out of the bag and told you that W0 is 2 to the power n, because that's the sum over all spin configuration of the number 1. So that simply counts the number of spin configurations. And we can write this expansion for the partition function by pulling W out, and you see I'll have this W1 by Wm by W0 and so on. Now we can now adopt a diagrammatic representation of these terms. So what is this diagrammatic representation? So this is the first non-zero term will occur, of course, at t to the 4, as we have seen. So t to the 4 W4 is represented in a picture as n times this quantity. So every time you see this blue line here, that's a power of t. And this W value is simply, in this context, it's simply the degeneracy of this, this link picture. If you look at other terms, you will get, you'll probably get different answers. So let's look at t to the 6th term. So t to the 6 little w6 will be 2n times this diagram, because I didn't discuss capital W6 diagrams, but this is the only diagram that will survive at W6 when I have 6 links. Let me go to W8. Please note there's a typo here. This should be W8. This is t to the 8 W8. 2n times this term plus 4n times this term plus n times that term, and n times n minus 5 by 2 times that term. So you will end up getting a term like this. This is the term for W8, right? So now you see the general result is that if you look at disconnected diagrams, again they will have degeneracies which scale as the number of power n to the power number of connected pieces. So this is a very general feature that shows up in all of these. Okay, so we are now ready to evaluate the partition function. So I just write all the terms. So that divides. So now I have taken W0 as 2 to the n and divided that, taken that to the left hand side, and I just get an expansion for the partition function. So you get something like this. So if I treat this as a small parameter called as x, because everything is some power of little t, and I remember to take the expansion of the log correctly to the correct order, you will again see magic working out, right? You will see that the free energy can be expanded in this fashion, and you will see again that you will get a linear term. This should be this minus sign should not be here. It's minus 5 by 2n and so on. So you will see this very nice expansion. Disconnected terms of higher power in n will be cancelled by powers of connected terms of lower order. That phenomena will continue to occur even in this expansion, and you will end up getting a correctly extensive free energy, right? So higher powers of n in disconnected diagrams will be cancelled by powers of connected diagrams, higher powers of connected terms. So now you will see that this expansion looks very much like the low temperature expansion, and this should surprise you. How can the low temperature and high temperature expansion look exactly the same? In fact, the coefficients, modulo my typos, right? There's a typo 4 here and there is a minus sign error, but please don't let that distract you from the main message here. You will see that this expansion is same as what we find for the low temperature, except some diagrams look different. So is this an accident or is there something deeper here? So in this slide, I'm going to submit to you that there is something much deeper and far more interesting here. So what is that? Here is the main message. Every high temperature diagram can be reinterpreted as a low temperature diagram in the dual lattice. So let me show you that by a picture. So think of the simplest high temperature diagram that contributed to a non-zero value to the free energy. Okay, so this is the low high temperature diagram, the blue picture. If I view this from the dual lattice, I can imagine that the dual lattice has a ferromagnetic state in which I had this central spin flipped. And remember, when we did duality, we identified these links of our lattice and links of the dual lattice that were crossing. So whenever there is a blue line in my lattice, which is the high temperature picture that I am looking at, I should also turn and make the link in the dual lattice in an excited state. So this high temperature term looks like a spin flip of a dual ferromagnetic ground state. This is the point. And now you can make a dictionary of this transformation. This is our model and this is what's happening in the dual. So if you think about this, you will see that that's the dual picture is there is a single spin flipped in the dual lattice. If you look at this, there are two adjacent spin flipped, and so all connected diagrams can be mapped to each other. And if you think about it for a moment, you will realize that the degeneracies are also exactly mapped. So there is a complete mapping between the low temperature and high temperature expansion. And the main point is, every diagram in the high temperature expansion has a partner in the low temperature expansion with the correct coefficient. Of course, this cannot be true unless you impose certain mathematical conditions associated with the value of this diagram and the value of this diagram. So the value of this diagram was little t, which was tan hk, and the value of this diagram was e to the power some k times something, right? So this was t to the power little t to the power 4, and this was e to the minus 8k or something like that. So if you match these values, you will see that the expression that you will get is t, which is equal to tan hk, must be e to the minus 2k star, which is the strong coupling. Remember, k, we are talking about the low temperature phase of the dual system. So the k has to be a very large number there, k star, I'm sorry. So this t has to be matched by that. But that's exactly the duality condition that we had discovered when we worked out the duality. Okay, so now you see the high temperature and low temperature expansion not only gave us insights into the physics of the ferromagnet and physics of the paramagnetic phase. We didn't calculate any physics of the paramagnetic phase, but you are welcome to do that yourself. You will see that it also provides this deeper insights, and actually you can actually realize why there is duality. So in fact, the physical insight that we are getting is the following. If you think about what these sort of diagrams at high temperature mean, they are sort of telling you some sort of ordering tendencies of my uncoupled spins. So you see my exact solution is uncoupled spins, that is k is 0. I am asking what is the physics when I have small k. So the idea is that there is some sort of ordering tendency of those spins, because there's some ferromagnetic interaction, so they want to sort of try to point together, and this diagram is sort of trying to capture that physics of trying to have some local cooperation to try to form some sort of order. The claim is this ordering tendency is equivalent if I view the same problem in the dual picture where I start at 0 temperature. So remember, the infinite temperature of our model will be the 0 temperature of the dual model. That will correspond to the defect. Remember, downspin flip is a defect in the ferromagnet. It's like a blemish. So ordering in my model corresponds to disordering in the dual model. So duality really connects order and disorder in a nice way. At least this is very clear in the Ising model. You can use these ideas to understand dualities in various systems. So this whole series expansion trick that we have explored, it not only gives us a tool to calculate, in fact, they were actually extensively worked on in the early days of statistical physics when people wanted to study phase transitions, etc. They also provide insights like what I just pointed out here. Okay. So we have come to the end of this chapter now, where we have discussed the Ising model extensively, and it's a good time to sort of take away some lessons from this study. So the main thing I would like to impose on you first and foremost is the importance of what spatial dimension, what role it plays in determining phases. So the Ising model, as we have discussed in terms of symmetry and energetics and all of that stuff, is the same whether you're in 2 dimension or 1 dimension. But in 1 dimension, you do not get an ordered phase at any finite temperature, whereas in 2 dimensions you do get. So you realize that spatial dimension plays a critical role. The other important concept is that when you have lots of degrees of freedoms that interact with each other, you can get emergent scales. Yes, the one-dimensional Ising model did not order at a finite temperature, but it produced a new length scale which is called the correlation length. The same thing happens in the 2-dimensional Ising model. We haven't computed it for the lack of time, I presume, but I'm sure that you can also try to compute it. And if you have written your Monte Carlo code, you can definitely use that to extract this emergent length scale and so on. Okay. The third big point is, when we discuss phenomena, we usually use some models which are motivated by symmetry and scales and so on. There may not be a single unique model that describes the physics that you want. You can have apparently different models with a connection of duality that will describe the same physics. The physics may be inverted in some sense. So in one model, something at high temperature will look like low temperature in the other model and so on. But there can be different descriptions of the same phenomenon. We have also learned many technical ideas which are useful for us to do calculations, to make quantitative estimates, to compare with experiments and so on. So for example, we learned the trick of defining link variables. That's an important trick of doing some sort of variable transformations. We learned about the transfer matrix approach. We learned series expansions and so on. So these are all very useful analytical tricks, and if you in your research or your work you're faced with any of problems related to the Ising model, you could try some of these tricks. Okay, so what's upcoming? So we have discussed the classical Ising model so far. There was no quantum mechanics of any kind, but Ising system, that is systems with local degrees of freedom that we have, they are also quantum versions of it. They are called qubits. So what we are going to do next is we are going to enter into the exciting regime of quantum systems. You will see quantum systems have many interesting ideas to offer, and I'm sure that given the promise of both applications and fundamental interest, you will join me for the next lecture. So thank you and see you next time.